So I want to go through two problems. I want to compare the solutions to the two. So again, it's just prove whether the series converges conditionally, converges absolutely, or diverges. And so problem 3 is going to be the sum k equals 1 to infinity of -1 to the k times k over 3k to the third plus 5, and we'll just go with plus 5, okay? Okay, so when we start this series, when we start trying to prove this series, we start by looking at the absolute value because it's alternating. So almost always that's what we're going to deal with. Later we'll have some other options, but for the most part, that's what we're going to do. We're going to say, okay, consider the sum of the absolute value of the original series. And then we're going to say, okay, that's equal to the sum k over 3k to the third plus 5. Okay, everybody clear how to start? Okay, we're going to consider, or now we're going to figure out what that series does. So on the ones that we did for the first two, when we took the absolute value, we were already at a p series. In the more general case, what's going to happen is when you take the absolute value, we now have a series with all positive terms. So chances are it's like what we were doing on series 3 on the homework from last night. Does that make sense? So look at this middle problem, this, and say, okay, if you were to do this problem as a brand new problem, what you would then do is you say, okay, they're all positive, and we would compare to the sum k over 3k to the third. Does that make sense? Everybody clear? We simplify that by pulling 1/3 out, and we get 1 over k squared. That series converges because it's a p series where p is 2, which is bigger than 1. Everybody clear on that part? Okay, now the series in the middle is going to do the same thing that the series on the right does. You can use either the limit or the direct comparison test to prove that. In this case, can I use the direct comparison, or am I forced to use the limit comparison on this middle series? So can we use the direct comparison?
Yeah, we can use direct.
We can, and we can because this one on the right converges, which means it levels off. We want the positive one to be smaller than that, and it is because the denominator is bigger. So we're going to say, okay, k over 3k to the third plus 5 is less than k over 3k to the third, and those are positive. So this middle one, and I'm just going to call it the sum of the absolute value of AK, converges by direct comparison. Does that make sense, everybody? We good?
Is the limit comparison test doable here?
You could.
Should be, right?
So yeah, you would be allowed in the middle here when I'm using direct comparison. You could instead use the limit comparison, and this would still converge. Does that make sense?
Yeah. All right, thank you.
Okay, yeah, no problem. Okay, now we've said now converges twice. So we've written converges over here, converges over here. What have we said in this proof? If you read carefully, what have we actually said about the original series so far? Nothing. We've said, okay, we don't like this, so consider the absolute value. We would rather deal with one that's all positive. This is all positive, so we compared it to something easier. We prove what the easier one does. We said, okay, now because this easier one converges, the comparison test tells us that the positive one converges. We've written nothing about the original, but if the absolute value converges, then what does the original have to do?
Merge as well.
Has to converge. So we go back and say, so the original series converges, and it converges absolutely because its absolute value converges to by the absolute convergence theorem. Does that make sense? Everybody clear so far? Okay, I want to look at another one that is very similar to that as far as the format. I'm going to put it in a different color just so I want to be able to compare these in a minute. But number 4 is going to be the sum k equals 1 to infinity of negative 1 to the k over 3k plus, we'll say, yeah, 3k plus 5. Okay. Okay, so based on what we did on the previous problem, we should start by saying, okay, consider the sum of the absolute value of AK. And so if you want to just write things a little bit quicker, I will assume if you write AK that you mean the original series, unless you tell me otherwise. Does that make sense? So if I want to shorthand it, I can write the sum of the absolute value of AK. That's equal to the sum 1 over 3k plus 5. Everybody good to hear? Okay, we're going to then compare that to the sum 1 over 3k, which is 1/3 times the sum 1 over k. Does that make sense? Okay, that diverges. Because it's a constant multiple of the harmonic series. Everybody clear? Any questions so far? Okay, now we're going to go back, and the one in the middle is going to do the same thing. So the one on the right diverges. It's positive, so it's going to infinity by diverging. The one in the middle, can I use the direct comparison, or do I have to use limit comparison?
You have to use limit comparison.
You have to use limit. We would like this one in the middle to be bigger, but because the bottom is bigger, it's actually smaller, so we have to use limit comparison. That doesn't change the conclusion, but it just changes the way we prove it. So we say, okay, 1 over 3k plus 5 is positive. 1 over 3k is positive. And now the limit as k goes to infinity of 1 over 3k plus 5 times 3k over 1 is the limit as k goes to infinity of 3k over 3k plus 5, which is 1. It's important that that's a number and that it's positive. And so the sum of the absolute value of AK diverges by limit comparison test. This is a little messy. Does that make sense? As I understand it. Okay, again, so like back up on the one on the top, we got the one on the far right converges, the one in the middle converges. The one on the left, because the absolute value converged, it converged as well. On number 4, the one on the right diverges, which means the absolute value, also the one in the middle diverged. But if the absolute value diverges, that does not tell us what happens to the original. Chances are it converges, and so we're going to use the alternating series test to prove that. BK for the alternating series test is 1 over 3k plus 5. You prove 3 conditions about that. First, bk is positive. You explain them. You just say they're true. The second is the limit of 1 over 3k plus 5 is 0 because it's 1 over infinity. The third thing is that bk is decreasing. And so on this one, it's simple enough to say, okay, 1 over or bk plus 1 is 1 over 3k plus 8. bk is 1 over 3k plus 5. And so because the numerators are the same and the denominator of the first one is larger, then that means the first one is smaller. And so because those 3 conditions are true, then the original series converges, but it converges conditionally because its absolute value doesn't. And we say it converges conditionally by the alternating series test. Does that make sense to everybody? Any questions so far?
Yeah, Doug.
Sure.
Where you did BK is decreasing, and then you did BK plus 1 equals 1 over
The 3k plus 8, Cheyenne?
how'd you get 8?
Because I'm replacing the k with k plus 1. So I'm doing, I'm doing 3 times k plus 1 plus 5. So it's like this, which is then 3k plus 3 plus 5. And that's where I'm getting 3k plus 8.
Oh, okay.
Does that make sense?
Yeah. Thank you.
Yeah, no problem. Does everybody follow that, where I'm getting that 3k plus 8? That's good. Other questions? Okay, so on almost all of these problems, so Max was asking a good question earlier, and this is something worth looking at. These are what the standard alternating series test problems look like, or standard alternating series problems look like. They're alternating because of either -1 to the k, or it could be -1 to the k plus 1. That would still alternate this series. The non-alternating part, so ignoring the -1 to the k, everything else is the same type of function. So like these are all power functions. Here, everything on the bottom, everything other than the -1 to the k, they're all power functions. They follow one of 3 types of problems. These are the 2 main ones. What you're gonna do is you're gonna take the absolute value, and then on the right, you're gonna get to this easier series. This part is going to be either a P series or a geometric series if all the function types are the same. So like other than the -1 to the k, if they're all power functions, you're going to get a P series here. If other than the -1 to the k, if they're all exponential functions, you're going to get a geometric series over here. Does that make sense? Okay, whatever this does, if this converges, then the one in the middle converges for sure. So these, the conclusion is the same. These 2, the conclusion is the same. If this diverges, this diverges. If this converges on the right, the one in the middle converges, no matter what. Does that make sense? You're going to use either the direct or limit comparison test for this middle part, okay? And it's most of the time, it's not like you get to pick the one you like better. Sometimes you have to use the limit comparison test. Sometimes you can use both. So like up here, we could have used the limit comparison test. We chose to use the direct comparison. It didn't matter. Down here, we had to use the limit comparison just because it wasn't bigger when we needed it to be. But you're going to use one of those 2 tests, and the conclusion will be whatever the conclusion was on the right. Does that make sense to everybody? Okay, if these two on the right both converge, so this converges, automatically this one converges. If that happens, then it converges absolutely by the absolute convergence theorem. So if these two converge, so if it's converge here, then this converges absolutely by the absolute convergence theorem every time. Does that make sense? If these diverge, so if this diverges, then this diverges almost every time. This is going to converge conditionally by the alternating series test, where you show these conditions. Does that format make sense? Those are the two big formats of problems on this next set of stuff. You guys good? Questions? Okay, now let's talk about a couple things with the alternating series test. So one thing is these three conditions would be true up here. So you could use alternating series test on problem 3. Okay. Why would we not need to use the alternating series test on problem 3? So what the alternating series,
two converge.
because the other two converge. Perfect. So because this converged, we know automatically that this converges. So there's no need to go through the alternating series test. If you do, you're going to get that it converges again, but we already knew that because this converged. Down here, you have to use it because when the absolute value diverges, that does not tell you what the original series does. Does that make sense? Okay, so there's going to be some questions that keep coming up and you should continue to ask them, and I will explain them again, and you should rethink about them again. It's weird. So one of the questions that will come up if you sit and do this homework is when you do the alternating series test, does it always converge conditionally? Technically, the answer to that is no, but every time that you should be doing the alternating series test, then it's going to converge conditionally. If you choose to do the alternating series test on problem 3, it would converge absolutely, but there would have been no need to do the alternating series test. Does that make sense? Okay, but if you do it when you're supposed to, then yeah, it would just converge conditionally. Another thing that's going to keep coming up is what if one of these 3 conditions is not true? And so let's talk about that. So down here, all 3 conditions were true, which meant this converged. Does that make sense? Okay, so let's go back up here and say, okay, what if this condition, BK is positive, weren't true? If that weren't true, then chances are it's probably not really alternating because you're taking -1 times something that might not be positive. And so it may not switch every other term, in which case none of this would apply. But on all these standard problems where everything is power functions or everything is exponential functions, the non-alternating part is going to be positive. Does that make sense? Okay. Of course, there are exceptions, but for the standard problems, that's not true. What if the second condition weren't true? So what if the limit of the non-alternating part was not 0? Why would we not be doing any of this if that was the case?
Because it would diverge according to the K-term test.
And it would diverge according to the K-term test. That's exactly right. So that's actually what I want to look at on problem 5. So problem 5 is the sum -1 to the k over the square root of 9k squared plus 1. This one, if you start doing it like the other problems, it looks the same, but when you get to the far right, you get the k's to cancel. So if you did get to this one, you'd be at k over the square root of 9k squared, which is the sum 1/3, and that should cue you in to something weird is going on. That means it's the K-term test. So you scrap this, and what you do is you say, okay, the limit as k approaches infinity of the absolute value of ak is the limit as k approaches infinity of k over the square root of 9k squared plus 1. That's the limit as k approaches infinity of k over 3k, which is 1/3 not 0. So the series diverges by the k-term test, or the test for divergence. Does that make sense? Everybody clear? Okay, I'll put that back up on the screen if we need to see it in a few minutes. But so if the first condition is going to be true if it's a standard problem, because if it's not, chances are it's not alternating. There's a chance it would all be negative, and we can talk about that, but you would just factor a negative one out. But basically the first condition is going to be true. The second condition, if it's not true, you should be using the k-term test. The whole thing diverges, and you don't do any of what we did on problems 4 or 5. Does that make sense? Or 3 and 4. You don't do any of that stuff. If the third condition isn't true, let's think about that. So if you think about a graph where everything is positive like the first condition, and it goes to 0, the graph basically looks like that. So if everything is positive and it approaches 0, most of the time it's going to be decreasing. Does everybody see that? So if the first two conditions are true, chances are it's decreasing. The case where maybe it's not is if you had something real weird where it was doing this and like kept bouncing but still approached 0. Does everybody see that? But that's not going to happen if it's -1 to the k times all power functions or -1 to the k times all exponential functions. So on normal problems, if the first two conditions are true, the third one is automatically true. That's not true in general, but that's true unless it's real weird. Does that make sense? Okay, so what that means is when we see problems like this, first check k-term test. If the k-term test works, it diverges. Otherwise, you follow this format. It's either going to converge absolutely because the two on the right converged, or it's going to converge conditionally because the alternating series test will hold. If the second condition is true, unless it's really, really, really weird, the third condition's automatically true. You have to still prove it, but it is true. Does that make sense? Any questions so far? Okay, so I want to talk about a couple things. One thing I want to talk about is this sheet. So this is a handout I would normally print out for you guys on like some obnoxious color paper. And I would ask you to keep it, and I would ask you to use it as far as the way to think about series. It's not one that you would normally be allowed to use on a test because it's not like a formal thing. It's the way you should think about approaching a series in general. Because your guys' stuff is open book, you can use this all you want. And so if you have a series in general, this is the way I would approach it in most cases. So the first thing you can actually look at is the k-term test or the test for divergence. If the limit of the sequence is not 0, then the sum diverges. Or you can use the version where if the limit of the absolute value is not 0, then the sum diverges. Does that make sense? Okay, then you've got these two basic series. So you've got geometric and p-series. Obviously, if it's one of those, you do those, but most of the other problems we're dealing with break down into those. So on the series sheet that you did on series 3, they were series with all positive terms. So this is a summary of what we were doing for yesterday and the day before. You get an easier series, which is called the comparison series. You figure out what it does. And so this is a little bit misleading. I should probably reformat this, but if the comparison series diverges, this is the thought process. It does not mean you always use the direct comparison. But what I'm saying is if the comparison series converges, if the original is smaller than the comparison, then use direct comparison, which is down here. Otherwise, use limit comparison, which is over here. Does that make sense? And then if the comparison series diverges, if the original is bigger, then use direct comparison, which is over here. Otherwise, use limit comparison, which is over here. That's for standard problems what we were doing on most of series 3. Now we're looking at a series with some negative terms, mostly alternating series. So first, you test the absolute value using the above test. So like if you go to those 3 parts, the first part is, or the middle part is you go to the absolute value, which is now one of these up here. If the absolute value converges, then the original converges. If the absolute value diverges, then you use the alternating series test. Okay, so as far as the way that the 3 columns worked out, as far as the, yeah, Pat, this is up on the eCampus. So if you go into the sequence series folder, this is there, and also the departmental one is there as well, which not because the departmental is not trying to be helpful, but it's the more formal sheet that has the conditions that you normally would be allowed to use on a test. I don't think it's very helpful, but it is available. And Sophia's asking Hayden, is this in your Dropbox? I will assume that Hayden will put this in his Dropbox. If not, I will. Okay, I have access to it now. Okay, so the 3 columns though, like if you looked back at the problems we were doing a minute ago, you have this column on the right, column in the middle, and column on the left. Column on the right is the basic series, geometric or p-series. Column in the middle is the absolute value, it's series with all positive terms. Column on the left is absolute convergence or alternating series test. Then at the bottom, we'll talk about ratio root test either tomorrow or Monday. Those are standalone tests. They're both easy, but unfortunately they don't work on most of the problems we're doing now. And then the integral test is the one we've been trying to avoid now for a week. And so that's the one you had to learn, but for the most part, you can get around the integral test. Okay, so this is in the Dropbox. I want you to obviously use that if at all possible. I want to talk about the homework that CrowdMark emailed you officially 1 minute ago. I want to pull it up and tell you guys to try to work some tonight. So it's called the Series 4 handout. If I can get it to open real quick, I will. Let's airdrop it and see if I can get it in there. Let's open ability. Series test summary. Okay. So here's the Series 4 homework. So the first several problems are ones where it's just a simplified version of those last 2, where once you start taking the absolute value, you're already at a p-series. Then we get into ones like the ones we're talking about on 3, 4, and 5. They're either they're absolutely convergent, where you do the 3 columns. They're conditionally convergent, where you have to do the alternating series test, or they're k-term tests, where you should just say, okay, diverges by k-term test. So 5, 6, and 7 are examples of that. 8, 9, and 10 are examples of that. And then when we start getting into 11, that's when it's different. So what I would like you to do tonight is get through problem 10. And normally I would love you to work ahead, but I do not want you to work ahead because we're going to learn more methods that will apply to 11 and on. So please try to get the first 10 problems done tonight and be really, really comfortable with those. We'll probably do a few examples at the beginning tomorrow where we might not go through the entire proof, but we'll talk about how to structure them, and then we'll move into the ratio and the root test. That's it as far as what I've got for today.